Hey guys, what's up? Eddie Alho here with KissAnalog.com. Guys, I'm going to show you that if you have one of these little small switching power supplies and you're afraid of the noise, or you want to get one, but you're afraid that there's noise, you see that switchy noise. When I've reviewed these in the past, I've explained that noise, I could put a little small capacitor right at the terminals and it gets rid of a lot of it right there. So it's just, a lot of it is just low energy. As soon as you hook it up to whatever circuit you're powering, that circuit's going to have an input filter that's going to pretty much kill most of that noise. But if you want a filter to do a little extra work on it and make it look a little cleaner, I'm going to show you something as low as a couple bucks. One thing I want to mention is this soldering station here. Hot air gun, soldering station. We had a winner. We only had 2 people ask for it. And so it was pretty easy to pick one. And so I got a winner. And we're going to send this out. Well, not this particular one. We're going to get a brand new one from the factory. They're going to ship it to the winner, so he doesn't have to pay shipping. Okay? And this one, I'm going to have my wife sell on her eBay store. I'm going to put a link down below if you guys are interested. There's a local paper here in Utah called KSL. She lists things there too. I have Oscilloscope. I've got some nice stuff there listed right now, but I think we'll put this one on there too. All right. Anyway, back to the video. So I'm going to bring you over to the bench right now. I'm just going to show you what we're doing. It'll be pretty simple, okay? And you'll see what it does. And then after that, I'm going to show you the schematic of it and the cost, and I'll have a link down below so you can buy these yourself, okay? All right, guys, let's come over to the bench, take a look. All right, guys, this is a matrix power supply. This is the MPS 3206, so 32 volts, 6 amps. All right, I'm going to set it for 10 volts, and we're going to just see how much noise is on this thing. It's a little small switcher. It's really nice. It's got all the memories. I really like this power supply, but it might have some noise. It might bother some people. But here, let's just show the other power supply. All right, this one's doing it too. For some reason, the flicker on, hey, if I put my hand in front, I notice it stops doing it sometimes. But I got this one set for 10 volts too. And this is the MPS WPS 300S-150-5. Anyway, 150 volt, 5 amp, or 300 watts, any combination of those things, okay? So we're going to, again, memories, a switcher, small for its size, very nice. Fan goes on sometimes, just like the other one, but normally it's off, so I like that. And I like this power supply a lot. I'll show this power supply in another video, but I really do like this. But it does put out a little bit of noise, okay? So we'll look at the output of this guy too. Now, I was going to use this active load, so I had it all hooked up. But, I thought, there's electronics in that. So I didn't want anybody getting confused with the noise that might be generated by an active load. So, ow, hot. So we're going to use this resistor, okay? Pretty non-inductive. It's for audio testing, so pretty nice. Twist these a little bit, and let's set up. All right, so yeah, if I hold my hand there, it might help a little bit. So I've got this set up for 10 volts. I'll hit the on button. I love power supplies that have an on button, and then it'll put power out to the cables here, which go right into my 4 ohm 200 watt resistive load, okay? And we'll measure noise right here. And what we'll do, we'll use this 500 meg scope, okay? So lots of frequency band. It's a UNI-T MSO3054HD, high def, so 12-bit, all right? It's right here, 500 meg, 2.5 gig, 12-bit. Okay, very nice. So I've got the spectrum set up so we can watch that. When you're looking at noise, it might, it happens at all different frequencies, right? So we'll look at the frequencies here, and we'll look at the spectrum here, so we'll see spikes here. And between the two, we should be able to kind of decipher how much noise we have. So 0 hertz to 1 meg, okay? And I've experiment a little bit. There's really not much noise past, out this way. It's mostly up in here. Okay, so let's connect up the probe, check it out. Okay, you can see I've got the probe, the ground twisted around the probe to make a small loop here as I can. The leads here are twisted. So I'm trying to keep all, pick up as, these acting like antennas as minimal as possible. Okay. And I think that's going to do it. So we come up here, I'm in channel 4, was going to use differential probe, had a more fancy setup, current probes and stuff. I thought, let's make this simple. Okay, so that's where we're going to be looking at. This is channel 4, and that's what we're seeing right now. Okay, that's without the load being turned on. That's just pickup from the power supply. And by the way, it's set at 1 meg AC coupling, full bandwidth, so we're not bandwidth limiting. Typically, when you're working with switching power supplies, use a 20 megahertz bandwidth limit. That's just a normal thing. But we're not. We're going full scale, okay? And so that's our setup there. Oh, and it's 100 millivolts per division, okay? So there we go. And you see 100 millivolts, full scale, 10x, all that stuff, all right? And we are reading the millivolts RMS, but, with this kind of noise, especially, well, you'll see. As it's spaced out at different frequencies, you get noise at different levels. It's hard to get a good RMS value because there's a lot of dead space in between the noise spikes. Okay, so over here, we have our table, okay? And I'm just going to put that right here. I'll just put it right up here, just in case we want to, if I see something interesting. So this is a marker. These little arrows here, those are the high points that this guy's reading. So the red is the peak signals that it's picking up across this frequency band. So we're seeing little spikes across here. And the blue is an average, four sweeps average. So not a lot of averages, but just something. So you can see it's kind of right in the middle. It's not quite as crazy as the red because it's an average. Okay, now this is the reference point right here, 0 dB. And we're all the way down here. That's minus 100 dB. So that is very, very low pickup, okay? But there are certain frequencies that are up around minus 80. So we're seeing minus 80. And that's probably this random noise over here that we're seeing, okay? Now, this is 50 microseconds per division. As part of the setup, I thought I'd show you the spectrum, okay? So the spectrum, if we come over here to general setup, channel 4, 0 to 1 megahertz, we're using the Hanning, and FFT 4 meg. So I've got that maxed out. So we're getting lots and lots of data points, okay? Decibel, 20 dBs per decade per division over here, and 60 dBs. We're offset 60, so that brings it 0, 60 dBs off of the center line here, okay? And then if I go to trace, we're going to look at the peak, okay? We're also going to average. That's these things down here I was telling you about. And I'm going to show you something else here in a moment, but we got 4 marker points. That's those arrows with the numbers jumping around, and that fills in this table over here. So, yeah, it's right now, we don't have any current going to the resistor, right? So it's just random noise jumping around. So let's go ahead and get something going. But, just before we do that, maybe I will go ahead and show you right now what we're going to do. See this maximum hold? This maximum hold, I'm going to say let's hold the average. So see that yellow line? The blue is the average, but the yellow is the hold. So every time it sees peaks, averaging 4 of them, it starts to hold that yellow. So that's kind of the, I guess, maximum average of all the noise. So there's minus 80 dB. So some spikes are above 80 dB, right? And the blue one is closer to, just above 100, or so maybe 95. But spikes and stuff, So you kind of see what it looks like, okay? That's with no power coming out. That's just kind of an electrical connection, mostly through a ground connection right now, okay? All right, so now this is all connected. I'm going to hit this power on button, but I'm going to bring you up to the screen because you'll see that yellow one change as I do that, okay? So I want you to watch for that. Okay, we're putting out 2.39 amps. And now you see the noise picking up, right, with the current flow. So the power supply is connected for one thing. The switch and the power supply is enabling power output. So we're actually connected to the input of the power supply now. So, or I mean, you know, to the output of the power supply, but through the switch. So now we actually have a connection into the power supply. So we're seeing that noise. All right, so interesting, right? So that's what we're seeing on the output of the power supply. So minus 60 dB, some of the spikes are above that. Over here, it's minus 66. So a lot of these are under. Minus 15 is the worst one. It's over here. Let's see, it's around 800 hertz. Yeah, so it's right along the border there. But the rest of them are kind of bouncing around. They kind of went over to this way. But all right, so that's what that looks like, right? Now, how can we fix that? How can we make that better? Okay, so that's the connection. Our resistor is going to be warming up. We got about almost 24 watts going into a 200 watt resistor, and you'd be surprised how hot that makes it. So, okay, so remember that. The solid yellow one is above minus 80. I'd say it's minus 70, minus 75, okay? And minus 60 is the peaks. And there's a lot of them. Most of them are in this half, up to 500 kilohertz. And then maybe up to 750. And the last, you know, couple hundred kilohertz, not much noise, right? I mean, not many spikes. So the flat part is what we call wideband. So it's a lot of areas, just the whole noise floor just coming up. And then the spiky, grassy things are actual frequencies that are jumping around, harmonics of the power supply, I'm sure. So anyway, that's what it looks like. Okay, hold on a sec. Let's fix that. All right, guys, you might be wondering how we're going to fix it. Well, we're going to put this in between the power supply and the load. It's 2 inductors and 2 capacitors. I'll show you the schematic in a moment. And it looks like, you know, I don't see a reference designator, so I don't know if those look like capacitors as well. Probably a couple little small ceramics right here, and parallel with the aluminum electrolytics. Pretty small. So I was going to say it doesn't have high frequency filtering, but it has a little bit. Large planes for the traces. I mean, you know, they're not really planes. They're just large traces, okay? We call them polygon traces sometimes, but anyway, there they are. These caps are just bent over. All right, let's hook this up. So we got to break our connection here. And put the thing, we'll keep the color coding, I guess. We'll put red on red. And black on black. Okay, there we go. I want to make sure I can get a scope probe on there. I can. All right, cool. So move that over this way, keep it in the camera, and then we'll hook this guy up. Red and black. Make sure I can get scope probes on those things. All right, guys. There's our connection, okay? Our low power supply in between. Let's go look at the screen again. All right, so that's what we're looking at now. It looks like it's dropped, but in the meantime, a bunch of stuff happened and it threw that yellow waveform up. So what we have to do is come in here and say max hold average, say off, turns it off. Then we'll say turn it back on. In some scopes I've had, it says clear, so you don't have to turn it on and off. Maybe there is a clear here. I just don't know where it is. So I'll just say average, turn it back on. And you can kind of see it there again. All right, so it looks a little bit better, but still pretty close to bad, right? Why is that? Well, I have the scope probe. Uh-oh. Well, for one thing, scope negative probe popped off. Let's go look at that again. It's clear that trace. Do off, and then turn it back on to average. There we go. That's looking better, right? Now, the amazing thing about this is we're measuring here at the scope from the power supply leads. So we're measuring right at the power supply. So why is that better? Well, this is one of the things I've been kind of explaining on my videos when I show these switching power supplies, and I say, hey, it's not really that bad, because when you connect it up to your circuit, there's going to be capacitors and stuff inside your circuit. That is a loading effect on the noise. So it loads the noise down and basically dissipates it, okay? Because there's filters, there's capacitors and stuff, even before it goes through all this stuff. Okay, now let's put the scope on the output side, see what it looks like. Let's go back up here again and look. So the line is right above the minus 100 dB line right there. It's right there. And then it goes above the minus 100 right through here. And so, see, here's 80. So it hits 90 over in here somewhere. But it's kind of sloping up. It's probably, I don't know, 1, 2, 3. It's four. It's still pretty close to 100 dB right here, and then it goes up. But, okay, so that's pretty remarkable, right? Just adding some capacitors on the output kills all that switching noise that we're worried about. So maybe it's not that big of a deal, but let's see if we can improve that. All right, so what we're going to do is take the scope probe off here and move it over here. A little tricky getting around the camera here. Okay, so we're connected, I think. Yep, looks like we're connected. I hope. All right, so let's go back to the scope here. All right, there we go. All right, so let's reset the hold. Let's go to off. Turns it off. Let's turn it back on. And look at that. Now we can clearly see the 100 dB line all the way starting. Some of the grass is spiking over through here, but it doesn't really catch up to the line until about here probably. So just by adding the filter, you know, just looking on the input side of the filter, it was already looking better, right? We weren't even looking at the output. Now we're on the output side of the filter and it even looks better. So, wow, pretty easy to fix. All right, guys, the fan's going on this. Can you hear it? I'll turn off my filtering on my post-processing so you can hear it. Oh, it just turned off. Man, I was talking over it probably. But it just sounds like a, you know, it's just not very loud. Shoot. Well, hopefully you can hear that. Okay, anyway, so let's turn it off. Take these leads out, which stick in there pretty tight. It's hard to get with one hand. Come over here, and they fit in here snug, but not as crazy tight. Okay, so... okay, this guy's already on, so he's already kicking out the power. I moved the probe back to the input side again. Now, look at this power supply. It's kind of interesting because 5, 6, 7, so 6, 7, 8, there's sometimes a bump. Now, if you watch, yep, there it goes. See, it started to go up. It's just every so often it starts to go up. It could be that that power supply we don't have loaded very much yet. But, yeah, anyway. And then there's some interesting... but, you know what? It's not fair. We got to reset it, though, right? Let's go do that. Off. Average. So, look how low it is. There's minus 100. So, without that bump being there, it's kind of like the input of the other one. So, you know, I'm right here, the input of the power supply, okay? So I'm looking right here. I'm not, and by the way, I haven't twisted these leads or twisted those. So that's kind of a more of a worst case thing. I should twist these and twist these to even make it better. But, so it's actually below the -100 right here, but then it kind of goes up and then it comes down. And it doesn't have quite as many spiky things, maybe, but it actually looks a lot like the other one when you just connect it to the filter. Okay, this is just the loading effects of any circuitry like a filter, you know, that has capacitors and so on, to whatever power supply you hook it up to. It's gonna, those capacitors are gonna load down that thing, and they're gonna load those high frequencies because they're shorting them, right? Those teeny ceramic, that's a teeny ceramic, but then we have aluminum electrolytic, so that's gonna help filter even before it goes through the board. Now the inductors are gonna help block it too, so that noise, when it tries to go through it, it's hitting the inductors and getting shorted through here instead. But we're looking at this side. Now when we go to the other side, we should see the benefits of all that. So let's do that. By the way, this is isolated voltages, so I could put my probe on, I could put my plus on what we're calling ground on the return, and I could put my, you know, I could switch the connections, my ground to the red, the tip to the black. It wouldn't matter, right? Because these are isolated outputs. It's just a voltage difference. Scope doesn't care if it's plus or minus. All right, so again, let's go turn that off, turn it back on, and see what we got. Wow, look, pretty much the same as the other power supply, right? Now, it is interesting. It pushes that little bubble up. Before it did that, it's still under -100 here, but it was under -100 all the way out here until it did that little bubble thing. And then the rest of it kind of looks like the other one. So they look very close, right? So here, let me reset that again, and we'll watch it for a second before that little bubble bumps up. Oh man, it seemed like it did it right as I reset it. It's funny because it doesn't happen very often, but it was just timed just right. So yeah, see how it's all under -100 all the way out here? Now we're gonna get that bubble thing happening. And that bubble is kind of a wide band, right? It's a lot of frequencies, so it's over a couple hundred kilohertz. So that's wide band. These little narrow ones are narrow bands. Now it's kind of funny. We have to wait a minute for this to happen again. Okay, just for fun, I'm going to turn my voltage up to higher because I know you guys are interested in what happens if you even put more power. My resistor is going to get really hot, so I've got 83 watts right now. So we did see some spikes, right? But here, now let me just start over and see where it is now, because it could have been me just, you know, changing the voltage. So see, still very good. There's a little bit more spikes, but right now we're at 83 watts. I'm going to turn the power back down because that's going to heat up my resistors quite a bit. All right, so I'll just turn it off. But yeah, so I think you can see the point, right? I mean, just adding a little filter, and this thing, I even have my thermal camera over there. I was going to show you, but I didn't even bother pointing out because it's just like, I'd say they're 30, 40 degrees. They're just warm, not hot. So I'll show you the specs on this guy. Okay, I'm going to show you the schematic because this guy is priced very well. I mean, it's a lot cheaper to buy this and modify it than to start from scratch, I think. All right, guys, I got my whiteboard here. Here we go. Now, there's a schematic, kind of. I don't have all the values. Now, the two aluminum electrolytics, they're 470 microfarad, 50 volt. These two ceramics, I'm not sure what value they are. They could be 1 microfarads, 0.1s, don't know. Have to remove them from the circuit to read them, so didn't bother. 22 microhenry, 22 microhenry, those inductors. So positive comes through one inductor and out, and then negative has to do the same thing. Why didn't they just use one inductor, 44 microhenry? After all, it's, you know, if you simulate the circuit, it'll work the same way. Well, I like this. I like to have isometric, or I like to have inductors on both sides. I like the circuit to look balanced. I think there's some benefit to that, so you don't have a straight conductor where a little bit of noise on this, common mode noise or whatever, could get right through. I like to have impedance on both legs, and as noise comes this way, hits those inductors, it's going to want to go through the capacitors. When it goes through the inductors, then out to the output, then you got some hold-up capacitors for the output. So, and some filtering for whatever circuit over here might be causing some noise, or, you know, pulling current at some frequency. So you get filtering here for the load, plus you get this LC filter on this side. You know, conversely, if your circuit over here is causing noise, it's going to keep that noise from going this way. It's going to come hit these inductors, want to stay on this side. Okay, so yeah, I like this kind of balanced circuit. Okay, what do you guys think? Leave me your comments. Now, one thing is, it'd be very easy to add parallel capacitors to either one of these on the back side of the board. It'd be really easy to do that. It'd be easy to swap out the inductors for different inductors, higher current inductors if you wanted that. Now you got to worry about the traces too, but the traces look very heavy, so I think they can handle some current. But I've got some other filters I bought and for higher current applications. So if you guys like to see this, I can do more filters and show you how the other ones operate too at higher current values, and we can compare. So let me know. Give me your comments down below, okay? All right, guys, let's get back to the video. What do you think, guys? A little small board like that, put in a little box with some banana plugs on it so you can put power in, bring power out. It's funny because it says input and output, but as far as I can tell, it's a symmetrical circuit. Doesn't matter which way is input and output. You can replace capacitors with better capacitors if you want. Higher voltage capacitors. These are rated for 50 volts. So I thought this was, and it's rated for 4 amps, by the way. I put more than 4 amps. It didn't even get very warm. I didn't do it for a long time though. But you know, a lot of the power supplies, these dual outputs, a lot of the power supplies, they're rated for 30 volts, and a lot of them are rated for 3 amps. So this guy should work great for that. Now, if you do have a higher current one, you could just put 2 of these guys in parallel, or you could swap out the inductors if you want to. You could, but yeah, it'd be easy, just put 2 in parallel, and you got 8 amps. And for, I think they're $2 a piece. Yeah, you get 5 for $10, $9.99 from Amazon. Put the links down below. Appreciate using those links. I get a little kickback, a little, you know, support for the channel, and so it doesn't cost you anything extra. So free way to support the channel just by using the links. But also just liking the video. If you like the video, if you'd like to see more videos like this, this is just a quick, easy, simple thing. I bought several filters to show you. I just chose the cheapest and simplest one for this video, but I was going to show you a couple others in this video. I decided to make it short, sweet, and show you the lowest cost that works quite well. So I didn't see the other more expensive one. It's not a lot more expensive, but it handles more current stuff. It didn't really do any better than this. So yeah, impressive. What do you guys think? Leave your comments down below. I'd like to hear it. All right, guys. So thanks for watching. 2 big thumbs up to my patrons, for my YouTube members, Danny for being a team member, and for hitting that super thank you button. Thanks, Danny. Appreciate that. You can hit that super thank you button down there. Buy me a cup of coffee, a beer for a rant. I am planning on doing a rant tomorrow, so I need a beer. Thanks, Danny. He bought me one. So, all right. Thanks for watching. And we're going to make sure that I got to make sure it's okay to show his name, so I didn't call him out, but congratulations on the new soldering station. All right, guys. Thanks for watching. We'll see you next time.